Welcome to the Explainer. Today, we're popping the hood on enterprise-grade Java code to see exactly what makes it tick. We're going to track the complete lifecycle of this incredibly robust language, the same one that's out there powering everything from massive financial systems to global telecommunications. To kick things off, we really have to ask, how does code actually run on any device? Specifically, how does Java pull off its famous write once, run anywhere magic across so many completely different platforms? I mean, translating our human intent into physical electronic actions is a massive leap, right? So let's break down exactly how Java bridges that gap. Here's our quick roadmap for today. We've got 1, the setup toolkit, 2, the transformation, 3, the execution engine, 4, the memory custodian, and finally, 5, modern Java. All right, section 1, the setup toolkit. Let's build our foundation. Okay, let's untangle those 3 acronyms that everyone always seems to mix up: JDK, JRE, and JVM. We can actually use a really simple factory analogy for this. Think of the JDK, the Java Development Kit, as your entire construction toolkit. It literally has everything you need to develop, compile, and debug, including the Java compiler. Now, inside that kit sits the JRE, or Java Runtime Environment. That's essentially your factory environment, bringing all the necessary libraries and support structures. And finally, nestled right at the core is the JVM, the Java Virtual Machine. This is the actual factory floor where the real execution happens. Moving right along to section 2, the transformation, going from human to machine. You can think of your code's journey like a 5-step assembly line. First, you write your program in a .java file. Second, the Java compiler, or JavaSec, steps in to convert that source code. Third, the JVM loads that newly created file right into memory using a class loader. Fourth, the JVM acts as a bouncer, verifying the code for security and correctness. And finally, step 5, it executes, turning it all into machine code for the final output. Now, the absolute crucial point here is that step 2, the compiler, does not actually make machine code. It creates this intermediate code called bytecode, which gets stored as a .class file. Guys, this is Java's absolute secret weapon for flexibility. Because bytecode is platform independent, you don't need to hunt down a different compiler for Windows, Mac, or Linux. You just use one compiler to generate the bytecode and then let the specific environment handle the rest of the heavy lifting. Okay, section 3, the execution engine. Let's step inside the factory. Right at the center of this whole operation is the JVM. Like we said, it acts as this abstract factory floor. And it's called virtual because, well, it doesn't physically exist. It's actually a specification that provides the runtime environment. Different companies, like Oracle for instance, take that specification and build the actual implementations so that the bytecode can run perfectly on your specific hardware. But here's the thing, the JVM is not just passively running your code. It's actively policing and translating it at the exact same time. It handles loading everything into memory, but critically, it verifies that bytecode to ensure it's completely secure before it ever lets it execute as native machine code. It is literally the ultimate gatekeeper and translator, all wrapped into one package. And I absolutely love this fascinating little detail because it shows how the JVM is constantly evolving. When you use modern functional programming tools like Lambda expressions, the Java compiler doesn't just generate a bunch of bulky new class files. Instead, it emits an invoke dynamic instruction. The runtime uses this to just spin up a suitable implementation right on the fly. It's such a brilliant, efficient way to handle modern programming paradigms without bloating up the whole system. All right, section 4, the memory custodian. Time for some cleanup. If you want to write code that doesn't completely crash your server, understanding stack versus heap memory is absolutely fundamental. The stack is built for fast, highly organized execution. It holds your local variables and keeps track of method calls. And the second a method finishes, boom, its local variables on the stack are instantly destroyed. But the heap, that's a dynamic pool. It's where all your Java objects live. And because these objects can be referenced by multiple different parts of your program, they don't just magically disappear when a single method wraps up. They require active cleanup. Which brings us to a massive trap for beginners, perfectly highlighted in the renowned book Effective Java. Look, just because Java cleans up after you does not mean you can't accidentally cause a memory leak. Think about it like this. If you build a custom stack and pop an item off just by moving an index pointer, the underlying array might still hold a reference to that object. Because that reference still exists, Java has absolutely no idea it's obsolete, and that memory is never freed up. You have to explicitly nullify those references yourself. But thankfully, We have our hero, the garbage collector. It's this automated custodian that works tirelessly to keep your application from just suffocating itself. It continuously scans the heap memory, hunting for objects that no longer have any active references pointing to them. And the moment it finds them, it reclaims that memory space. This means you absolutely do not have to manually delete objects like you would in C or C++, which is a feature that has literally saved developers from countless, maddening hours of manual memory management errors. And finally, Section 5, Modern Java. The future is now. You know, it's easy to forget, but Java's internals are not frozen in 1995. They are actively evolving, stripping out old, dangerous processes. Take the old finalize method, for example. It was highly unpredictable and could cause deadlocks or security vulnerabilities, so it was actually deprecated in Java 9 in favor of much safer cleaners. Then, jump to Java 21, and we're seeing massive performance leaps with the Z garbage collector. This thing cleans new and old memory concurrently without ever stopping your application threads. And looking ahead to Java 25, we are getting a simplified execution model where you won't even need an explicit class declaration just to run a basic program. It's getting so incredibly streamlined. Now, Project Loom, which dropped in Java 21, completely revolutionizes concurrency. Traditionally, every single Java thread mapped directly to an operating system thread. That's incredibly heavy and severely limits how much you can scale. Virtual threads totally change the game. They are lightweight, managed entirely by the JVM, and scheduled onto a small pool of real OS threads. This means you can now run literally millions of tasks synchronously. And when one pauses to wait, the JVM seamlessly detaches it and runs something else, all without ever locking up your physical operating system. It's a real game changer. Oh, and if you're coming over from a language like JavaScript or Python, you are going to absolutely love JShell. It stands for Read, Eval, Print, Loop. It brings that fast, iterative, scripting language feel right into the Java environment. You can literally just type 5+3, hit enter, and immediately see 8. No need to define a class, no need to write out a whole public static void main method. It's just an incredible tool for instantly testing how internal Java logic evaluates on the fly. I'm going to leave you with this thought to ponder today. If the JVM is now capable of managing millions of virtual threads while concurrently cleaning memory without ever stopping our applications, what is the next big bottleneck software engineering will have to conquer? Is it the network? Is it the database? The factory floor itself is now so highly optimized, the real challenge has clearly moved elsewhere. Thank you so much for joining me on this explainer, and keep exploring.